The paper discusses the optimization of synthetic data for enhanced pancreatic tumor segmentation, a crucial step in improving clinical decision-making for this leading cause of cancer-related mortality. It highlights the limitations of existing generative AI-based frameworks and proposes a series of experiments to test specific hypotheses, particularly investigating the impacts of synthetic tumor size variation and the precision of tumor boundary definitions on tumor segmentation accuracy. The authors note that selecting an optimal combination of tumor sizes is crucial for achieving superior segmentation outcomes, and precise tumor boundary annotations significantly enhance model performance. They also explore potential reasons for the unsatisfactory performance of pancreatic tumor segmentation models with tumor synthesis under real-world scenarios. In their analysis, they evaluate the influence of tumor size and nonperfect tumor annotations, pointing out that the size of synthetic tumors significantly influences the training of segmentation models. Pancreatic tumors are relatively small compared to the entire pancreas, presenting a considerable challenge for segmentation. The study leverages current tumor generation tools, including rule-based approaches, autoencoder models combined with latent diffusion models, and generative adversarial networks, GANs. It emphasizes the importance of utilizing refined synthetic data augmentation for enhancing the clinical utility of segmentation models in pancreatic cancer decision-making, including diagnosis, prognosis, and treatment plans. The paper discusses the optimization of synthetic data for enhanced pancreatic tumor segmentation. It highlights the challenges in generating realistic synthetic data, particularly due to the small size and variability of pancreatic tumors. To address these issues, the authors propose two hypotheses. Utilizing different synthetic tumor sizes can improve segmentation performances, and more accurate tumor boundaries lead to better performances. The authors utilize a tumor generation network based on the DiffTumor framework, which processes input volumes through an encoder, integrates them with a tumor mask, and then uses a latent diffusion model and decoder to produce the final synthetic volume. The segmentation model is trained using both dice loss and cross-entropy loss. The dataset used includes the MSD pancreas dataset for real tumor data, along with samples from the pancreas CT and BTCV datasets as healthy controls. To verify the first hypothesis, the authors controlled the tumor size during the generation process by analyzing tumor volumes from the MSD pancreas dataset and categorizing them into 4 predefined size classes: tiny, small, medium, and large. These quartile-based radii replace the initially predefined radii to ensure an accurate representation of natural tumor size variations. To verify the second hypothesis, the authors refined tumor boundaries through elastic deformation, introducing a randomized, nonlinear transformation to the synthetic tumor regions. This is achieved by manipulating a grid of control points, where the grid spacing and displacement amplitude are adjusted to simulate realistic tumor shapes and boundaries. The authors also propose a new metric, the Boundary Precision Index, BPI, to evaluate the accuracy of the generated tumor boundaries. The paper concludes that optimizing synthetic data for enhanced pancreatic tumor segmentation can significantly improve the performance of segmentation models. By controlling tumor sizes and refining boundaries, the authors aim to create more realistic synthetic data that better represents the variability observed in real-world datasets. This research has implications for improving the accuracy and reliability of automated segmentation tools in medical imaging. Optimizing synthetic data for enhanced pancreatic tumor segmentation involves using elastic deformation to create more realistic tumor boundaries. This process, applied to both the tumor regions and their labels, enhances segmentation performance. The research focuses on validating the hypothesis that synthetic data can improve segmentation accuracy. To achieve this, the authors partition the MSD pancreas dataset into training and testing subsets and use a 4:1 ratio. They apply data augmentation techniques and train models like UNet, NNUNet, and SwinUNetter on an A100 GPU for 200 epochs. The results show a clear improvement in segmentation performance for all models when synthetic volumes are utilized, particularly with larger synthetic tumor sizes. This indicates that larger synthetic tumors might be more effective in improving model accuracy. The incorporation of synthetic volumes significantly enhances the model's ability to accurately segment tumors, as evidenced by the more precise delineation of tumor boundaries. The research paper discusses the optimization of synthetic data for enhanced pancreatic tumor segmentation. It compares the performance of UNet, NNUNet, and SWIN-UNetter models on various levels of noise in the labels. The study highlights the critical importance of accurate synthetic tumor boundary generation to mitigate the adverse effects of label noise and improve model performance. The authors demonstrate a marked degradation in segmentation accuracy as the noise level in the labels increases, emphasizing the need for high-fidelity synthetic data. The findings suggest that future research should focus on developing more sophisticated methods for generating synthetic data that closely resembles real-world pathological presentations. The paper discusses optimizing synthetic data for enhanced pancreatic tumor segmentation. It begins by referencing various studies on medical segmentation, including the medical segmentation decathlon and synthetic data generation. The authors highlight the importance of high-quality synthetic data for training deep learning models, citing works on generative adversarial networks and diffusion models. They emphasize the need for data that accurately mimics real-world scenarios, mentioning the challenges of segmenting pancreatic tumors from computed tomography, CORT, scans. The paper then delves into the methodology used to generate synthetic CT scans, focusing on the use of cellular automata and pseudolabels for semi-supervised learning. It concludes by discussing the benefits of this approach, including improved model performance and reduced data collection costs. Throughout, the authors draw from a wide range of research in medical imaging, AI, and computer science to support their arguments.